In 1977, NASA launched Voyager 1 with a small gold record attached to its side. On it were sounds of Earth, laughter, music, greetings in dozens of languages, and a simple message meant for whoever or whatever might find it. It was humanity's quiet attempt to say, "We were here." More than 40 years later, that message is still traveling. Voyager 1 has already left the solar system, yet it hasn't even crossed a single light year, and so far, no one has answered. We like to imagine space as a vast emptiness, but in that small bubble around our sun, there are dozens of star systems and a growing list of worlds we've detected, suspected, debated, and sometimes had to take back. Some were once hailed as second Earths, only to be questioned by the same science that announced them. Some are blazing stars like Sirius, bright enough to dominate our night sky. Others are stellar corpses like Sirius B, dense remnants of stars that lived fast and died young. And some are frozen planets circling ancient red dwarfs, worlds that may exist only as faint, mathematical fingerprints. This is not a traditional astronomy lecture. Think of it as a map of real nearby worlds within 20 light-years of Earth, stitched together by one theme: death, desolation, and the silence of the universe. We'll move outward in layers, from the nearest stars to once sensational systems like Gliese 581, from overhyped hope to careful discovery. And along the way, we'll ask a quieter question. In all this silence, what are we really listening for? The map begins small, not with the galaxy, but with a fragile sphere of space around our star, drawn quietly in the dark. Imagine placing the sun at the center of an invisible bubble and letting that bubble grow until its edge is 20 light-years away. In human terms, 20 light-years sounds almost intimate, like the distance between neighborhoods on a cosmic scale. Within that bubble, astronomers have catalogued roughly 90 star systems and on the order of 130 individual objects. Stars, white dwarfs, and brown dwarfs drifting together through the same thin patch of interstellar medium as us. Most of them you will never see. Only a small fraction, maybe a couple of dozen at most, are bright enough to rise in our sky without help from lenses and mirrors. The rest stay hidden in the black, discovered not because they shine strongly, but because telescopes know exactly where to look, and for how long. On a screen, the 20 light-year bubble is a simple thing. A sphere, a scatter of points. Some dots cluster together where multiple stars share the same gravitational well. Others are alone. If you did not know what you were looking at, you might mistake it for a minimalistic piece of art. A handful of lights caught in a dark room. But each dot is a star, or more than one star. Some are red dwarfs, small and cool compared to the sun, the cosmic background class that dominates our neighborhood. Some are white dwarfs, the dense remains of once larger stars that burned through their fuel and then collapsed into cinders the size of a planet. A few are more familiar, brighter, more massive stars that already have names you might recognize from stargazing guides. The bubble feels crowded when we list it that way. 90 systems, around 130 objects. That is more stars and substellar bodies than you will encounter in a lifetime of naked-eye stargazing. It is easy to imagine that such a neighborhood must be lively, busy, full of potential homes and watchers. Then we add scale. Our galaxy, the Milky Way, stretches for roughly 100,000 light-years from one side of its disk to the other. The 20 light-year bubble around the sun barely scratches that surface. If the Milky Way were a city spanning a continent, our mapped region would be the space just outside your front door, a step off the threshold that does not yet reach the street. The visual shrinks us. This entire bubble, full of catalog entries and coordinates, is only a thin shell inside a much larger structure of spiral arms, star clusters, gas clouds, and dark matter. From far enough away, the difference between 0 light-years and 20 light-years becomes negligible. The bubble disappears into the texture of the disk. From close-up, though, that missing distance is everything. Take Voyager 1, launched in early September of 1977. It has been traveling outward for nearly half a century. It has long since passed the orbits of the outer planets. It has crossed the heliopause, the fuzzy boundary where the influence of the sun's solar wind fades into the broader interstellar medium. Even so, at the end of the year 2025, Voyager 1 is only a few tens of billions of kilometers away, something like a fraction of a single light day from the sun day. A light year is the distance light travels in 1 year. A light day is that distance divided by roughly 365. After decades of uninterrupted flight, our fastest interstellar messenger has not yet reached even that smaller milestone. If we waited for it to cover a full light year, we would need tens of thousands of Earth years at its current pace. Set that against the 20 light-year bubble. Every star inside that sphere is 20, 30, 40 times farther than a single light year. The closest system beyond our own, the Alpha Centauri trio with Proxima Centauri tagging along, sits over 4 light-years away. At Voyager's speed, reaching just that first ring of stars would take tens of thousands of years. Our front yard is not simply large, it is effectively unreachable on any timescale that feels human. So when we call this a neighborhood, we are already bending language. A neighborhood on Earth implies walkability, shared streets, windows across from each other glowing at night. The 20 light-year bubble has none of that. Each star is a house separated from the next by vast stretches of nothing, without roads, without signals, without even the faint smoke of a distant chimney to show that someone is burning fuel inside. If someone were there, we tell ourselves, we might have heard them by now. That assumption hides in the way we talk about these stars. We give them names. Barnard's Star, Wolf 359, Ross 128, Epsilon Eridani. We imagine them as neighbors because their light reaches us quickly enough that we can still call it nearby. But light traveling for 10 or 15 years is not nearby in any practical sense. It is only nearby compared to the rest of the galaxy, where light might wander for tens of thousands of years before reaching our telescopes. Inside this bubble, our instruments have found a growing list of planets, super-Earths, mini-Neptunes, temperate candidates skimming the edges of what we call habitable zones. Some orbit red dwarfs so closely that their years last only days. Others move in wider, colder paths, where starlight is a weak and distant thing. Many of these worlds exist for us only as wobbles and dips, small shifts in starlight that betray an orbiting mass, little more than a line of numbers in a catalogue. Those lines can feel deceptively hopeful. An Earth-sized mass, an orbit within the zone where water might, in principle, remain liquid. A star not too different from others we trust. We look at those parameters and instinctively translate them into narratives. Maybe an ocean, maybe clouds, maybe continents, perhaps even cities spreading under an alien sky. But when we look for actual voices from these places, the data stay flat. Radio surveys have swept past many of the stars in this bubble, listening for narrowband, artificial-looking signals. Searches in visible light have looked for unusual, repeating flashes. So far, nothing unambiguous has come back. The stars themselves are noisy in their own ways. Flaring, pulsing, rotating. The universe offers plenty of natural beacons. Yet against that background, there is no clear whisper of technology, no repeating message that says, here too someone is listening. The 20 light-year bubble is therefore a strange object. On one level, it is crowded. We are not alone in the trivial sense of being the only star in an empty volume. On another level, it is profoundly solitary. Every other point of light is so distant that, for now, it might as well be behind glass, like a window you can see but never reach. Picture it again, not as numbers, but as an image. The sun at the center. Around it, a transparent sphere, its radius labeled 20 light-years. Within that sphere, roughly 90 small points of light, representing star systems. Perhaps one point is colored differently to mark Alpha Centauri, another for Barnard's star, a few brighter ones for Sirius and Procyon, many more barely visible, representing cool red dwarfs and brown dwarfs that never rise above the threshold of human sight. The screen is mostly black. You could stare at that map and see richness, so many worlds, so many orbits, so many chances, or you could stare at it and see separation. Each tiny island isolated by distances that turn decades of travel into almost nothing. In this series, we will treat that map as a kind of quiet star chart of absence. Each point on it will become not a promise of another Earth, but a case study in what it means for a world to be silent. Some will be places where physics itself seems to forbid biology as we know it. Some will be places where the physics looks permissive, yet no evidence of life reaches us anyway. Some will be worlds that existed only as statistical phantoms before dissolving back into noise. For now, hold on to the image: a dark sphere, a scatter of mute lights, and our own star at the center, humming with life and radio traffic, trying hard to be louder than its size would suggest. This is our immediate cosmic neighborhood. Not empty, not welcoming, a cluster of lit windows in the night, and not a single one has opened to answer. If no window ever opens, eventually we stop calling it shyness and start wondering whether anyone lives there at all. That is where the phrase "dead world" begins to creep in, quietly, without a clean scientific line to support it. We use it as if it were simple, as if there were a checklist somewhere that could tell us with certainty which worlds are alive, which are sterile, and which are simply refusing to speak loudly enough for us to hear. In practice, we have three different languages for the same idea. The first is physical. A world is dead, we say, if the basic conditions for life as we understand it are broken at the root. A surface baked to thousands of degrees, or plunged into permanent cryogenic cold, an atmosphere stripped away by stellar wind, leaving bare rock exposed. A planet tidally locked so that one hemisphere is cooked endlessly, while the other lies in eternal night. These are the places where chemistry itself seems to congeal, where complexity has nowhere to begin. The second is observational. A world is dead, in this sense, if it never answers. No radio beacons, no unnatural flashes in the night, no spectral fingerprints of disequilibrium gases in its air, no oxygen paired with methane, no biosphere-sized metabolism altering the way starlight filters through its atmosphere. It could be rich with microbial life. It could even host forests or oceans. But if all of that is hidden from our instruments, it is observationally dead to us, no more responsive than a stone. The third is emotional, and it is the least honest and the hardest to avoid. We call a world dead when it does not fit the story we hope to tell about it. Proxima b sits at the crossroads of these meanings. The planet orbits the nearest star beyond the Sun, a small red dwarf a little over 4 light-years away. In terms of mass, Proxima b is close to Earth, perhaps slightly heavier, and its orbit keeps it in what we would normally label the habitable zone, the shell around a star where liquid water could exist on a rocky surface. On paper, that sounds promising. The details are less kind. The planet orbits its star at a distance far smaller than the one between Mercury and the Sun, completing a year in a little more than 10 Earth days. At that distance, tidal forces almost certainly have locked one face into permanent day and the other into permanent night. Above that endlessly sunlit hemisphere, Proxima Centauri is not a calm, steady star. It is a flare star, prone to violent outbursts of ultraviolet and X-ray radiation that can spike many times higher than the star's normal output. Over millions or billions of years, that kind of bombardment can strip away atmospheres, especially from planets that sit so close. When Proxima b was first announced, it carried headlines as a potential second Earth, a near twin in the habitable zone of our nearest stellar neighbor. In the years since, as we have learned more about the star's flare behavior, that optimism has cooled. The more we understand Proxima Centauri, the more likely it seems that Proxima b is either an airless rock, its atmosphere long since blown into space, or a world with a thin, altered envelope of gas, scorched and chemically reshaped by its star. If oceans ever formed there, they may have boiled away or been broken apart into escaping hydrogen and leftover oxygen long ago. So, is Proxima b a dead world? On the physical side, we do not know enough to be certain. It might retain a strong magnetic field that shields its atmosphere. It might have begun with a much denser blanket of gas, thick enough to survive eons of flares. Under those conditions, life in some form might still be possible, perhaps in an ocean under heavy clouds, or in a twilight band around the edge of the day side where temperatures are less extreme. On the observational side, it is entirely mute. We cannot resolve its surface. We cannot separate its light cleanly from the glare and fury of its star. We have no spectrum of its air, if it has air at all. We cannot hear any technology, even if it is there. Proxima b exists to us primarily as a wobble in the star's motion and as a set of orbital parameters. It is a label on our map. Emotionally, its story has already shifted once. First, it was a symbol of hope. Then a kind of warning about the cruelty of red dwarfs. That shift did not come from new images or clear biosignatures. It came from our own evolving expectations, from how we choose to weigh the same sparse data. Barnard's star B tells a different version of the same problem. Barnard's star itself is another red dwarf, smaller and dimmer than Proxima, drifting through space at a distance of nearly 6 light-years. It is old, perhaps twice as old as the Sun, a quiet, slow-burning ember of a star. When astronomers announced evidence for a planet there, they described a super-Earth with a minimum mass around 3 times that of our planet, circling at a distance where sunlight would be weak and temperatures far below freezing. In simple terms, Proxima b is a world that may have been burned. Barnard's star B is a world that seems to have been frozen from the start. Its orbit takes roughly 2/3 of an Earth year. At that distance from such a faint star, the planet's surface, if it is solid, might sit tens of degrees below zero even in the warmest regions. Any water would likely be locked in ice. Any atmosphere, if present, could be thin and cold, perhaps dominated by carbon dioxide or nitrogen, hugging the ground against the vacuum. There is no reason to think of it as a likely home for oceans and forests. Yet again, much of this is inference, layered on top of limited data. We do not know whether Barnard's star B has moons. We do not know the exact composition of its surface. We do not have a spectrum of its air. Like Proxima b, it appears in our catalogues as a set of numbers: mass, orbital period, semi-major axis, equilibrium temperature. The rest is extrapolation. From a purely physical standpoint, Barnard's star B is not absolutely forbidden territory for life. Extremophiles on Earth thrive in brine pockets, inside Antarctic ice, in high-pressure cold environments at the bottom of the ocean, in subglacial lakes cut off from sunlight for hundreds of thousands of years. A sufficiently thick atmosphere, or a subsurface ocean insulated by ice, could in principle harbor chemistry on Barnard's star B that never sees the light of its star. From an observational standpoint, the planet does not exist to our senses at all. We have no direct way to image such a small, dim world so close to its parent star. Its presence is a subtle shift in the star's velocity, teased out from years of precise measurements. If we could somehow switch off the data analysis and simply look, even with our best telescopes, we would not see it. This brings us to a third kind of dead world, one that is stranger than the burned and the frozen. Gliese 581 became famous because of this kind of ambiguity. For a time, it was one of the most talked about planetary systems beyond the Sun, a red dwarf just over 20 light-years away with several known planets. Among them, one candidate stood out: Gliese 581g, a supposed super-Earth orbiting in the middle of the habitable zone. When its discovery was announced, it was immediately framed as a serious contender for a second Earth, a place where liquid water and temperate climates might be possible. Then the reanalyses began. Other teams looked at the same radial velocity data and argued that the signal attributed to planet G could be an artifact of noise or of the star's own activity cycles, rather than a genuine planetary pull. Some models of the system kept the planet, others made it vanish. The more carefully people dug into the evidence, the less certain its existence became. If Gliese 581G is not there, was it ever meaningful to call it a world at all? For a while, it existed powerfully in our imagination. Artists painted skies for it. Writers speculated about its climates. Headlines presented it as a near twin to our planet. Then, gradually, it retreated into the status of a disputed signal, a statistical fluctuation. In that sense, it is a dead world of a different kind, one that only ever lived as a pattern in our data and in our hopes, and then dissolved when those patterns were questioned. So, what do we really mean when we say dead world in this map of nearby stars? We do not, and cannot yet, mean biologically confirmed lifelessness. We have no direct photographs of these surfaces, no samples of their rocks, no sniffed atmospheres, no detected fossils. Even in our own solar system, we argue about whether Mars, Europa, or Enceladus might harbor some form of life in hidden niches. Around distant suns, our ignorance is greater still. We also do not only mean physically impossible. A planet scorched by its star could, deep below the surface, hide pockets of relative safety. A frozen super-Earth could shelter an ocean beneath kilometers of ice. Our imaginations are quick to populate these unseen spaces with hypothetical microbes. What we can say, honestly, is something narrower and colder. In this context, a dead world is any world that has no voice we can hear. It is a place that, given our current tools and understanding, remains silent, either because it is truly sterile or because whatever life it may hold does not shout loudly enough across the light years to register above the noise. It is also any supposed world that flickers briefly into existence as a signal and then collapses when we look more carefully. Some of these dead worlds may one day surprise us. Some may never be more than footnotes in old datasets. For now, they share one property that matters for our map. When we point our antennas and instruments toward them, nothing answers back. If every other point on the map stays silent, the only voice we can really study is our own. The sun is where that voice begins. Not in some abstract way, but in the most literal sense. Every burst of radio, every television broadcast, every radar ping that has ever left Earth has been powered by energy that started as fusion in the sun's core. The heat in our air, the winds that carried our early antennas, the food that kept the engineers alive long enough to build transmitters. All of it is sunlight, delayed and transformed. Out of all the stars inside that 20 light-year bubble, the sun is the only one we know for certain has a planet wrapped in a shell of chemistry that has been radically altered by life. Its light arrives here with the same indifferent precision it would have for any barren rock. What we do with that light is what turns this system into something noisy. When we talk about other stars, we lean heavily on this one. The sun is our first grammar for understanding what a star is allowed to do. Deep inside, under layers we will never touch, its core is a place of crushing density and temperature. There, at something like tens of millions of degrees, hydrogen nuclei are pushed close enough together to fuse into helium, releasing energy in the form of high-energy photons. Those photons scatter and bounce their way outward through the radiative zone, a region where light diffuses slowly, tangled in a dense plasma. Above that, in the convective zone, the star starts to behave more like a pot of boiling water than a smooth ball of light. Hot plasma rises, cools, sinks again. Enormous cells of motion carry energy up toward the surface, where the temperature has fallen to a few thousand Kelvin, still hot enough to turn rock into vapor, but cold compared to the interior. Outside what we see as the surface, the sun extends further into a tenuous, ghostly atmosphere called the corona. Paradoxically, this outer layer is far hotter than the surface below it, reaching temperatures of 1 to a few million Kelvin, a fact that puzzled solar physicists for decades and still does not have a completely settled explanation. We know these details because we are close, and because we care. We have watched the sun in every wavelength we can manage. We have listened to its interior vibrations through helioseismology, reading standing waves on its surface the way geologists read seismic waves inside Earth. We have measured the gusts and lulls of the solar wind, the stream of charged particles that constantly flows outward, carving a bubble in the interstellar medium. And we have flown spacecraft straight into the region where that wind is born. On a night in mid-August, in the year 2018, a heavy rocket rose from the Florida coast, carrying a small, heat-shielded probe built to fall toward the Sunday. That spacecraft, later known as Parker Solar Probe, was launched by the United States Space Agency with one task: to dive repeatedly into the Sun's corona, skimming only a few million miles above the visible surface. Over the course of its mission, using repeated gravity assists from Venus to tighten its orbit, it has become the fastest object ever built, swooping closer to our star than any previous spacecraft, and sampling the charged particles and magnetic fields of the corona directly. Seen from the quiet stars around us, none of this is visible. The Sun would appear as an ordinary yellow dwarf, slightly brighter than many, slightly fainter than some. Its spectrum would show the same hydrogen and helium lines as countless peers. The odd behavior of its corona could be inferred, but not in detail. You would not know about the tiny metal object repeatedly looping through the heat. Listening. From where we sit, though, the Sun is not just another entry in a catalogue. It is an engine we have come to know intimately enough to lean on as a reference. When we say a red dwarf is small and cool, we mean small and cool compared to this star. When we talk about habitable zones, we mean distances where a planet would receive roughly the same amount of energy that Earth does from the Sunday. The unit we use for orbital distance, the astronomical unit, is simply the average space between Earth and the Sun, about 150 million kilometers, or a little over 8 light minutes of travel for a photon. That distance is also the scale of our earliest noise. In the early 20th century, humans learned to generate radio waves and send them out intentionally. At first, the signals were local curiosities, dots and dashes in Morse, laboratory experiments, military communications. As the technology matured, the broadcasts grew more continuous and more powerful. For roughly a century, our planet has been leaking radio, television, radar, and now a constant haze of data into space. If you draw a sphere centered on the Sun, with a radius equal to the distance that a century of radio waves could have traveled, the result is far larger than the 20 light-year bubble we have been mapping. Every star we are talking about lies well within that expanding shell of human noise. From their point of view, if anyone were there to have one, our Sun would not only be a star, it would be the center of an expanding radio storm. A thin, chaotic shell of artificial emission riding on top of the natural radio waves that planets and stars produce on their own. Against the quiet hiss of the cosmic microwave background and the sporadic crackle of natural radio sources, there would be faint, structured patterns. Carrier waves, modulated signals, narrow bands that turn on and off in ways no known natural process does. We do not know how easy it would be to detect that shell. Our own surveys of the sky are limited by our instruments, by the interference from our own infrastructure, and by the short amount of time we have been listening. But conceptually, the Sun is already a beacon of a kind. It is the only star in our neighborhood that has definitely begun broadcasting in a way that is not purely astrophysical. The irony is that we almost never talk about the Sun as a message. We talk about it as a problem. Solar flares can knock out power grids. Coronal mass ejections can damage satellites and force astronauts to seek shelter. The same solar wind that carves a protective bubble against some interstellar radiation also batters our magnetosphere and paints auroras in the sky. Space weather forecasting has become an applied science because this star is not a distant abstraction for us. It is a constantly changing environment we live inside. That closeness is why we have sent machines like Parker Solar Probe into harm's way. It is also why we sent other machines in the opposite direction, away from the Sun, into the dark. Voyager 1 and Voyager 2 were launched in the late 1970 seconds to tour the outer planets. Their trajectories, assisted by the gravity of Jupiter and Saturn, eventually bent them onto paths that would carry them out of the solar system altogether. Decades later, Voyager 1 has crossed the heliopause, the boundary where the solar wind yields to the thin gas between the stars, and is now moving outward at a speed of a few astronomical units per year. At that pace, it will take on the order of many thousands of years to cover a single light year. On board Voyager, one is a small golden record, a metal disc engraved with sounds and images from Earth. Greetings in many languages, music, natural noises like thunder and surf, and a diagram showing where our sun sits among nearby pulsars. It is not a practical communication system. It is a keepsake, a token of the fact that one of the planets circling this star has learned to speak in symbols. From a certain angle, this is what differentiates the Sun from every other dot in our 20 light-year map. Not its mass, not its temperature, not the exact shape of its corona, but the fact that there is a thin film of matter on one of its planets rearranging itself into machines that send information outward on purpose. If an astronomer around another star had instruments like ours and time like ours, they would see hints of this. They might notice that Earth's atmosphere is oddly rich in oxygen, a reactive gas that would vanish quickly without a continuous source, and that traces of methane persist alongside it, an unstable pairing that suggests ongoing chemistry beyond simple volcanic outgassing. They might see nighttime lights on the dark side of our planet as a faint modulation in reflected starlight. They might, with sensitive enough receivers, pick up the narrowband spikes of our transmitters. To them, our Sun would be the only star in their own local bubble that obviously hosts a world out of equilibrium with simple geology. To us, it can be hard to feel that specialness. The Sun is our default background. It rises every morning and sets every evening. We complain about its heat, worry about its storms, and take its stability for granted. Its 11-year magnetic cycle, with its waxing and waning sunspots, is something we track because of satellite communications and long-range power lines, not because we expect the star itself to do anything dramatic on human timescales. We forget that its quiet is unusual. Comparisons with other stars tell us that the Sun is, if anything, more stable than many similar dwarfs. Its luminosity varies, but not wildly. Its flare activity is significant, but not catastrophic. Its rotation period is moderate. All of that has given life on Earth a relatively calm stage on which to emerge and evolve. In that sense, the Sun's most important message is not in its bursts and eruptions, but in its reliability. Yet even this reliability has an expiration date. Stellar evolution models tell us that in a few billion years, the Sun will exhaust the hydrogen in its core, swell into a red giant, and radically transform the inner solar system. Earth's biosphere will not survive that transition in anything like its current form. The noise will stop. The radio shell will continue expanding, but the source will have gone quiet. For now, though, this is the only place in our 20 light-year neighborhood where physics has clearly crossed the line into biography. The same nuclear furnace that powers flares and coronal loops also powers a thin, restless layer of complexity on a small, rocky planet, a layer that has begun to turn matter into message. When we speak of dead worlds around other stars, it is this contrast we are really using, whether we admit it or not. A dead world is one that, as far as we can tell, has no equivalent to this. No thick chatter of signals, no global change in atmospheric chemistry driven by life, no artifacts flung into interstellar space with music carved on their surfaces. Inside the 20 light-year bubble, surrounded by quiet stars and silent planets, the Sun stands out as the only confirmed source of that kind of noise. It is an ordinary star, but it has become, for now, the only star that we know can carry a conversation, even if its words are only just beginning to escape into the dark. The first other window we look toward is the one closest to us, the faintest dot that still counts as a neighbor. Proxima Centauri is that neighbor. On star charts, it sits as a small companion to the brighter Alpha Centauri pair. But in reality, it drifts a little apart, a dim red dwarf a bit more than 4 light-years from the Sunday. In terms of pure geometry, it is the nearest star beyond our own. In terms of experience, most humans will never see it with their eyes. It is too faint, too red, too easily drowned in the glow of our own sky. Seen from a distance, the Sun and Proxima Centauri would be two ordinary stars sharing a wider orbit around the center of the galaxy. One yellow, one red. One bright enough to dominate a local sky, the other barely visible. There is nothing obvious in their light alone to tell you that one hosts a biosphere and the other is suspected of hosting a single rocky world in a dangerous embrace. That world is Proxima Centauri b. When it was first announced, in the middle of the second decade of the 21st century, the headlines were simple and irresistible. Here was a planet roughly similar in mass to Earth, orbiting within the region around its star where liquid water might exist. It belonged to the nearest star system. It was a short step from there to the phrase, nearest potentially habitable planet. And then to all the imaginative leaps that follow those words. The reality behind that phrase is quieter and harsher. To begin with, Proxima Centauri itself is not a scaled-down version of the Sunday. It is smaller, cooler, and much dimmer. Its total power output is only a small fraction of the Sun's luminosity. To receive a similar amount of energy to what Earth gets, a planet must orbit extremely close in, hugging the star in a tight, swift path. Proxima b does exactly that, circling its star at a distance that is only a few % of the distance between Earth and the Sun, and completing a full orbit in a little more than 11 Earth days. At that distance, gravity does more than simply hold the planet in place. Over time, tidal forces tend to lock the rotation of the planet to its orbital period, the way the Moon's rotation is locked to its orbit around Earth. One hemisphere becomes the permanent day side, facing the star with the same face over and over. The other hemisphere becomes a permanent night side, turned away from the light forever. On a theoretical map of Proxima b, there would be a blazing hemisphere under a tiny but fierce red sun that never moves from the sky. A frozen hemisphere buried in endless darkness and a narrow band of twilight in between, where the star clings to the horizon and the temperature, if an atmosphere exists, might hover somewhere between extremes. Even this mental picture is more detailed than what our instruments can actually see. We do not have an image of Proxima b. We cannot resolve it separately from its star. We know it is there because of the way Proxima Centauri itself moves, rocking gently toward and away from us under the pull of the orbiting mass. From that wobble we infer a minimum mass, a distance from the star, and a period. Everything else is extrapolation, built from models. What complicates the picture further is that Proxima Centauri is not a calm host. Red dwarfs in general are known for their flare activity, and Proxima is no exception. Observations over many years. Invisible light, ultraviolet, and radio and millimeter wavelengths show that the star frequently erupts in violent flares, sudden bursts of energy that can increase its brightness dramatically for minutes or hours at a time. These flares are rich in high-energy photons and in charged particles, the kind of radiation that can break apart molecules in an atmosphere and strip the lighter elements away over long periods. For a planet that sits so close, each major flare is like a nearby nuclear detonation in the sky. The day-side atmosphere is hammered by ultraviolet and X-ray radiation. Ionization rates spike. Chemistry is reset. If the planet has a magnetic field as strong as or stronger than Earth's, it might deflect some of the charged particles and protect at least parts of its atmosphere. If it does not, the star's wind and flares can slowly peel the gas away, exposing the surface to vacuum. Studies using arrays like ALMA and space telescopes sensitive to high-energy light have caught Proxima Centauri in the act of producing flares that carry many times the energy of the most intense solar flares ever recorded from our own. Every star. On the Sun, such events are relatively rare. On Proxima, they appear to be a regular feature of its behavior. For any world in the putative habitable zone, that behavior is not a detail, it is the environment. From our current distance and with our current tools, we cannot say which outcome has played out on Proxima b. It might be an airless rock, its original atmosphere entirely blown away, its surface baked and then directly exposed to space. It might retain a thick, dense atmosphere, perhaps rich in heavier molecules, that has survived the onslaught. It might hold volatile materials in a subsurface ocean or ice layer, shielded under rock. Our definitions of habitability are stretched thin here. On paper, the planet receives a level of stellar flux that could, with the right conditions, allow liquid water to exist. In practice, the climate depends on a long list of unknowns: the initial inventory of water and gas, the strength of the magnetic field, the structure of the atmosphere, the composition of the surface, the intensity and spectrum of flares, the long-term stability of the orbit. So far, the only thing that Proxima b has definitely been hospitable to is human projection. When people first heard nearest Earth mass planet in the habitable zone, they imagined oceans under a red sky, perhaps strange trees silhouetted against a never-setting star. When later studies highlighted just how violent Proxima Centauri's flares are, the same world was recast in darker tones: a burned, stripped planet, a cautionary tale about red dwarfs and wishful thinking. Between those two images lies a vast space of uncertainty. We do not know whether any life could endure in the twilight band of a tidally locked world under such a star. We do not know whether life, if it arose, would find ways to adapt to constant ultraviolet bombardment, perhaps sheltering underwater or underground, or whether the chemistry needed to begin life is simply too fragile in such an environment. What we can say, with more confidence, is that if any technological civilization had arisen there and started broadcasting loud, deliberate signals in the same way we do, we have not yet heard them. Multiple surveys have listened in the direction of Proxima Centauri across a range of radio frequencies, looking for narrowband beacons or artificial patterns. So far, the only signals we detect from that patch of sky are the star's own natural emissions and the occasional interference from our own machinery. In spite of that silence and that hostility, Proxima has become a primary target for our long-term ambitions. When a group of scientists and entrepreneurs stood up in New York City in the middle of the second decade of this century and announced a project called Breakthrough Starshot, the destination they named was the Alpha Centauri system, with a particular eye on Proxima and its planet. The idea was simple and extreme at once: build tiny gram-scale spacecraft with reflective sails. Hit those sails with an enormous array of ground-based lasers and accelerate the probes to a significant fraction of the speed of light. At perhaps a fifth of light speed, a probe could cross the space between the Sun and Proxima Centauri in a few decades. A message sent back at light speed would take a little more than 4 years to return. In human terms, that is still a lifetime of waiting. In astrophysical terms, it is almost immediate. The project remains a concept, a roadmap, rather than a built fleet. The engineering challenges are immense. The lasers would need to be coordinated across vast distances. The sails would need to survive tremendous accelerations without tearing or melting. The tiny instruments on board would need to operate autonomously after decades of flight in deep space. But the choice of Proxima as a first destination says something about how strongly distance shapes our imaginations. We look out at a galaxy, tens of thousands of light-years across, and we fixate on the system that is just over 4 light-years away, not because it is welcoming, but because it is the place where the numbers feel least impossible. We tell ourselves that if we can reach one nearby world, any world, the others might follow. Concept studies have gone further, imagining vast generation ships that would carry human populations on multi-century journeys to the same general destination, turning the space between the stars into a habitat in its own right. Those designs are speculative. They assume technologies we do not yet have, social systems we have never tested, and resources we have not committed. Still, they orbit the same focal point, a small red star and its battered planet. In that sense, Proxima Centauri and Proxima b have become a mirror for our hopes and our limits. The system is close enough that we cannot ignore it, harsh enough that we cannot easily romanticize it, uncertain enough that we can project almost anything onto it. From the perspective of our 20 light-year map, Proxima marks the first ring of silence beyond the Sunday. It is the closest place where there might have been another conversation, another world reshaping its own atmosphere and sending signals into the dark. Instead, what we see is a star that behaves like a restless ember, flaring and cooling, and a planet that shows itself only as a tug in that star's motion. We keep listening. We model the flares. We refine our measurements of the orbit. We dream of sails, driven by light. All the while, the system itself goes on as it has for billions of years, indifferent to our designs. In the end, Proxima Centauri is not a promise of refuge. It is a reminder, the very nearest, potentially Earth-like world on our map, the one that feels almost within reach, sits next to a firestorm. Just beyond that fire, the brighter part of the same system hangs in our sky like a promise we keep rewriting. Alpha Centauri is what most people think of when they hear the phrase nearest star. Not the dim red ember of Proxima, but the bright double star visible from southern latitudes, low over the horizon like a lantern just out of reach. Through a small telescope, that single point splits cleanly into two. Alpha Centauri A star slightly larger and hotter than the Sun, and Alpha Centauri B, a little smaller and cooler. Together they form a close binary, circling a shared center of mass in a long, slow dance that takes roughly 8 decades to complete. On a human timescale, that means an entire lifetime is enough to watch the geometry between them change wide apart in one generation, tighter in the next, the angle between them shifting against the background constellations. On a galactic map, the pair sits only a little farther from us than Proxima, a bit over 4 light-years away. They are the closest stars that look, at first glance, like our own. For centuries, that resemblance has been enough to turn Alpha Centauri into a kind of default destination in our stories. Once people realized that the bright point near the Southern Cross was a nearby system of sun-like stars, it became the natural stage for imagined colonies, alien civilizations, interstellar expeditions. If there were going to be neighbors, many assumed, they would live there. The physics of the system seemed to encourage that intuition. 2 main sequence stars, both stable and long-lived, each with its own region, where a planet at the right distance could receive sunlight comparable to what Earth enjoys. Theoretically, each habitable zone could host rocky worlds with temperate climates, oceans, atmospheres, perhaps even continents, and weather patterns comfortingly similar to our own. The orbital separation between Alpha Centauri A and B changes over time, but on average the 2 stars are only a few dozen times farther apart than the Earth is from the Sunday. That is wide enough that each star can have its own family of close-in planets without those orbits being immediately torn apart, but close enough that each is a bright object in the other's sky. If you stood on a hypothetical planet around Alpha Centauri A, Alpha Centauri B would shine in your heavens much more brightly than any star shines in ours. A permanent second sun with its own rising and setting. On paper, this configuration looks almost too perfect. Nearby, sun-like, potentially rich in habitable real estate. For a long time, the lack of confirmed planets there felt less like data and more like an omission waiting to be corrected. Popular culture stepped into that blank space long before measurements did. In the film that made the moon Pandora famous, the world orbits a gas giant around Alpha Centauri A. Audiences watched humans breathe alien air under a pale, familiar star, and accepted, without much question, that, of course, the first lush exomoon we would visit would be in that nearest bright system. The story did what stories do. It filled the unknown with something that felt emotionally right. Actual observations were slower and more stubborn. Finding small planets around bright, close binaries is technically difficult. The 2 stars' spectra overlap. Their motions complicate the already delicate task of measuring tiny wobbles in radial velocity. For years, groups around the world tried to tease out hints of orbiting worlds in the Alpha Centauri system, refining instruments, revising methods, pushing the limits of precision. Then, early in the 2nd decade of this century, a team announced the detection of a planet around Alpha Centauri B. It was not an Earth twin, more of a hot, close-in world, but it was enough to trigger the reaction people had been waiting for. Headlines spoke of the nearest exoplanet to Earth. Even if the planet's surface was likely molten, its existence seemed to confirm that planetary systems around our closest neighbors were real facts, not just extrapolations. Within a few years, that certainty dissolved. Other astronomers reanalyzed the same data and found that the supposed planetary signal could be explained by subtle patterns in the noise and by the star's own activity. What had looked like a clean, repeated tug might have been an artifact of the analysis. Gradually, the consensus shifted from "we have found a planet" to "we are not sure there is one here at all." In the catalogues, the name of that world now often carries an asterisk: proposed, disputed, likely illusory. For a brief moment, it had a mass, an orbit, a temperature. It lived in artist renderings and press releases. Then it joined the growing list of ghosts, worlds that existed primarily in our desire to find them. More recently, attention has turned to other hints. A possible gas giant glimpsed in mid-infrared data around Alpha Centauri A, subtle excesses in light that might, or might not, be caused by a planet viewed in a particular orbital phase. Each candidate is announced cautiously, surrounded by caveats, and accompanied by plans for follow-up observations that will take years. Each one could, in principle, turn into the first clearly imaged planet in the habitable zone of a sun-like star beyond our own. Each one could just as easily fade back into the background, another pattern at the edge of what our instruments can reliably see. From the viewpoint of our map, the effect is strangely symmetrical. Around the dimmest member of the Alpha Centauri system, Proxima, we have planets whose existence is firm but whose surfaces are probably brutal. Around the bright pair, A and B, we have a long-running rumor of planets that might be real but have not yet been pinned down beyond doubt. Meanwhile, the stars themselves continue to burn steadily, indifferent to our shifting levels of confidence. Alpha Centauri A, slightly more massive and luminous than the Sun, radiates with a pale yellow-white glow. Its spectrum is familiar. Its outer layers convect and churn in ways that echo the patterns we see on our own star. Alpha Centauri B, a bit cooler and more orange, contributes a steadier, softer light. Their mutual orbit takes them from closer than the distance between Saturn and the Sun to farther than the distance between Uranus and the Sun, over and over again, in a slow gravitational loop that has been repeated countless times since before humans existed. If there are rocky planets tucked into the safe zones around these stars, they have spent hundreds of millions of years bathed in fairly gentle light. Tides from the companion star might rock their orbits slightly, but not enough to rip them away. From the standpoint of long-term climate stability, the configuration is not obviously hostile. And yet, as far as our telescopes can tell today, there is no clear, unambiguous sign of a living world there. No atmospheric spectrum with a screaming imbalance of gases. No technosignature. No narrowband radio beacon sweeping across our frequencies on a precise, repeating schedule. If Alpha Centauri hosts an inhabited planet, its inhabitants have either chosen to remain very quiet, or their technological footprint is so different from ours that we would not recognize it as a signal at all. Despite that lack of evidence, Alpha Centauri continues to attract mission concepts the way a nearby mountain attracts climbers. Proposals for interstellar probes, generation ships, swarms of laser-pushed sails, many of them point first to this system. The reasons are obvious. The distances, while immense, are the smallest they can be and still count as interstellar. The stars are familiar types. The chance that planets exist there is high, even if we have not yet catalogued them all. In this way, Alpha Centauri has become the closest door on our mental hallway out of the solar system. We keep telling ourselves that if we can find a truly Earth-like planet anywhere, it will be here. We design missions around that assumption. We set our fictional stories under its light. We speak about it with a kind of proprietary anticipation, as if we are already half moved in. The data, so far, do not cooperate with that feeling. Every few years brings a new wave of papers, a new set of velocity curves, a new instrument promising better contrast. Each time, the conclusion is similar. There might be small planets in stable orbits in the habitable zones of Alpha Centauri A or B, but no one has yet produced a detection robust enough to stand alone. The absence is not proof that such planets do not exist. It is instead a measure of how thin the edge is between what we hope to see and what we can actually measure. Seen in that light, Alpha Centauri is less a promised refuge and more a carefully framed emptiness. It sits at the center of a web of human plans, physics calculations, launch concepts, novels, films, and speculative art. It is the most modeled, most imagined star system beyond our own. And yet, when we strip those layers away and ask what we really know, the core is simple. Two stars, orbiting one another. A third, dimmer star, loosely bound far away. No confirmed Earth-like planets. No confirmed biosignatures. No confirmed messages. From Earth, on a clear night in the southern hemisphere, Alpha Centauri shines brightly enough to cast a faint shadow. To the naked eye, it looks steady, solid, almost reassuring. Navigators once used it as a reference. Farmers timed their planting by constellations in its neighborhood. It feels, in other words, like a landmark. In our silent map of nearby stars, though, it marks something else. It is the place where all our technology and all our stories have converged. And the universe has responded with a shrug. Not a hostile one. Not a welcoming one. Just the kind of indifferent quiet that space seems to specialize in. We keep watching that bright double star as if we were standing outside a house at night, staring at lit curtains, listening for movement inside. Decade after decade, the lights stay on. Shadows move in ways we can almost, but not quite, interpret. Now and then someone claims they heard a voice, and then the wind picks up and drowns it out. The house is close, closer than any other that looks this much like our own. But the door, if there is one, has never opened. The house that will not open sits in one direction. In another, there are lights that seem to move of their own accord. Barnard's star is one of those moving lights. On paper, it is a small, dim, red dwarf, a little under 6 light-years away. The second closest individual star system to the Sun after the tangled Proxima Alpha Centauri trio. It is not impressive in brightness or size. What makes it strange is how quickly it seems to slide across the sky. In the early years of the 20th century, the American astronomer Edward Emerson Barnard compared photographic plates taken years apart and noticed that one tiny point had shifted more than the rest. By 1916, he had measured its motion as a little over 10 arcseconds per year, the largest proper motion known for any star. Over the course of a human lifetime, that adds up to roughly half the apparent width of the full moon. Most stars seem fixed. Barnard's star crawls. Through a telescope, the star itself is unremarkable, a faint ember in the constellation Ophiuchus, far below the threshold of naked eye visibility. Yet, if you could take a time-lapse of the sky over decades, speeding up human history into a few seconds of film, you would see that ember drift against the background, threading its way between slower, more distant lights. It is as if one of the fixed stars had slipped its anchor. On our map of nearby space, that motion gives Barnard's star a particular kind of presence. It is not just close, it is obviously going somewhere, a neighbor passing by rather than a distant building on the horizon. Its path through the galaxy will eventually bring it even nearer, to within roughly 4 light-years in some tens of thousands of years, before it moves on. For early exoplanet hunters, this made Barnard's star an irresistible target. A nearby red dwarf, with a clear, measurable trajectory through the sky, seemed like the kind of place where a planet, if it existed, might be easier to detect. For decades, astronomers pointed spectrographs and photometers at it, hoping to see the tiny periodic wobbles or dimmings that would betray an orbiting world. Hints came and went. In the mid-20th century, there were claims of giant planets. Later, observations did not support them. The star kept moving. The data stayed ambiguous. Then, in the second decade of the 21st century, a team announced what many had been waiting for: evidence of a super-Earth. Barnard's star B, inferred from subtle variations in the star's radial velocity. The proposed planet had at least a few times Earth's mass and orbited in roughly 2/3 of an Earth year, at a distance from the star near the so-called snow line where any surface water would be frozen and the equilibrium temperature far below the freezing point of water. The picture that emerged was of a cold, dark world. The star itself is much dimmer than the Sun, so even at that relatively close orbit, the planet would receive only a small fraction of the energy that Earth gets. Without a thick atmosphere and strong greenhouse effect, its surface might sit at around -150 degrees Celsius. Hard ice, thin air, if any, a place more like a permanently dark outer moon than a warm terrestrial globe. That was the scientific side. On the emotional side, something else was happening. For a short time, Barnard's star B was everywhere in the news cycle. It was described as the closest known super-Earth, the first planet found around this long-studied neighbor, a milestone in the history of exoplanets. Artists rendered it as an icy sphere, lit by a dim red sun. Science communicators used it as a chance to talk about snow lines and radial velocity techniques, about long-term monitoring and the patience needed to find small signals. Then, as with Gliese 581G, the reanalysis began. Over the next few years, other teams took the same data, added new observations, and modeled the star's intrinsic activity more carefully. In that refined picture, the periodic signal that had been attributed to a planet could instead be explained by changes in the star's own magnetic cycles and surface features. In 2021, a detailed study concluded that Barnard's star B was almost certainly not a real planet, but an artifact of stellar activity. The candidate was effectively withdrawn. Barnard's star kept moving. The supposed world that had briefly orbited it in our imagination did not. There is something fitting, if quietly unsettling, about that. The star with the largest known proper motion hosts, in our current understanding, no confirmed planets at all. The only world we had given it in the modern era turned out to be a ghost, a ripple in the data that dissolved under closer scrutiny. Our map has to be erased there, the ink lifted off the page. Wolf 359 offers a different kind of ghostliness. Where Barnard's star is noticeable in motion, Wolf 359 is defined by its absence from ordinary human experience. It is a red dwarf in the constellation Leo, at a distance of a little under 8 light-years, making it one of the closest stars to the Sun after the Alpha Centauri system and Barnard's star. Yet, despite that proximity, it is utterly invisible to unaided eyes, with an apparent brightness far below what our retinas can pick up. Spectroscopically, Wolf 359 is an extreme example of a cool M dwarf. Its surface temperature is only a few thousand Kelvin, low enough that molecules like water and titanium oxide can form and survive in its atmosphere. Its mass is a small fraction of the Sun's, only a little above the threshold needed to sustain hydrogen fusion at all. It is also a flare star. Observations show that its magnetic field is hundreds of times stronger than the Sun's mean field, and that it experiences frequent, intense flares that can increase its brightness dramatically for minutes at a time across optical, ultraviolet, and X-ray bands. In that sense, it has something in common with Proxima Centauri, a restless, violent surface, a tendency to erupt. In 2019, analyses of radial velocity data suggested that Wolf 359 may host at least 2 planets, both more massive than Earth, in relatively close in orbits. If they are real, they are almost certainly subject to the same harsh conditions that plague planets near Proxima: tidal locking, intense flaring, and climates far from anything we would instinctively label as friendly. Unlike the case of Barnard's star, these planets have not yet become famous enough outside specialist circles to carry much emotional weight. For most people, Wolf 359 does not exist as a physical place at all. It exists as a line in a script. In the fictional universe of Star Trek, the Battle of Wolf 359 is a pivotal trauma, a catastrophic engagement with an implacable enemy. Fought in the early years of the imagined 24th century, referenced again and again as a symbol of loss. The episodes that first depicted it aired in the year 1990, but the event itself is placed centuries ahead, in a future where humanity moves casually between stars. The real Wolf 359, the actual star, is unaware of this. It flares and cools, rotates and drifts through the galaxy. Its faint light reaches our telescopes after traveling for nearly 8 years through space. The star does not know that, in our collective storytelling, its name has become shorthand for annihilation. That gap between the almost non-existent presence of Wolf 359 in our night sky and its outsized presence in our fiction is a reminder of how our minds fill in what our instruments barely detect. Barnard's star and Wolf 359 are, in that sense, paired ghosts. One is a moving ember with a history of illusory planets, a runaway star whose most famous world had to be erased from the books. The other is a nearly invisible dwarf that the actual sky almost hides from us, elevated to symbolic prominence by a story set in a future we do not inhabit. Physically, both are part of the same local structure. They share the Sun's general orbit around the Milky Way. They pass relatively near in cosmic terms, then recede. If you were to stand on a planet, real or imagined, around either star and look back, our own Sun would be just another bright point. Its slight yellow tint, indistinguishable from countless others. From that vantage, our dramas would be as absent as theirs are to us. No one there would see the erased echo of Barnard's star B in our datasets. No one would hear the dialogue about battles near Wolf 359. There would only be an ordinary G-type star in the sky, perhaps noteworthy only because it seems slightly more stable, slightly more luminous than the red dwarfs that dominate our neighborhood. On our side, when we put these stars on a 20-light-year map, they show us two different ways silence can have texture. Barnard's star is silent despite being scrutinized more closely than almost any other red dwarf. Its emptiness is active. We keep asking it for planets, and it keeps telling us, in effect, that our measurements are not yet good enough to be sure of anything small and Earth-like there. Wolf 359 is silent because we can barely see it at all. Its light is so feeble that it disappears into the background unless we deliberately hunt for it. Together, they outline a boundary condition for our search. There are stars we know well enough to say probably barren, or no obvious large planets so far, and stars we hardly know at all beyond their basic properties. There are worlds we thought we had found and had to abandon, and worlds that exist only in scripts and sets. When we speak of ghosts in this context, we are not being poetic for its own sake. We are acknowledging that much of our map is drawn in pencil. Some points will sharpen into solid planets with measured masses, radii, and atmospheres. Others will be rubbed out, leaving only the memory that, for a while, we believed there was something there. Meanwhile, the stars themselves keep moving, tracing their long paths through the galaxy, indifferent to the lines we draw between them. Some ghosts are almost invisible. Others are so bright they wash out everything around them. Sirius is the second kind. On a clear night in the right season, it is the star your eyes fall to, even if you are not looking for anything in particular. Low in the sky, it seems to shimmer more than the others, its light passing through thick air near the horizon, breaking into brief flashes of blue, white, and faint red. People once read those colors as omens. Today we know it as optics. The effect is the same. Long before anyone called it Sirius, people along the Nile watched for the first dawn when this star rose just ahead of the sun, a fleeting appearance known as the heliacal rising. It came roughly once each year, in the weeks when the river began to swell and break its banks. For them, this star was tied to flood and grain and survival. Its return marked a new year. They gave it names that linked it to goddesses, to fertility, to a cycle that felt eternal. From our latitude in the galaxy, Sirius is bright because it is both intrinsically powerful and close. It lies at a distance of a little under 9 light-years, in the constellation we call the Greater Dog, which is why English speakers sometimes call it the Dog Star. That distance makes its light only a little older than the light from our own sun when it reaches us. In human terms, it is a neighbor. In galactic terms, it shares our spiral arm, drifting along the same vast track around the center. To the unaided eye, Sirius looks like a single point. With a small telescope and some patience, it resolves into a pair. The primary, Sirius A, is a hot blue-white star, significantly more massive than the Sun, and many times as luminous. Its surface seethes at temperatures higher than those of our own star. Its lifetime on the main sequence will therefore be shorter. Massive stars burn through their hydrogen more quickly. Around it, gravity binds a smaller, unseen companion in a long, elongated orbit that takes about half a human century to complete. That companion is Sirius B, and it is not a normal star at all. In the 19th century, astronomers studying the motion of Sirius A noticed that it did not travel through space in a perfectly straight line. Instead, it traced out a tiny looping path, as if pulled by an unseen hand. That wobble implied a partner. Eventually, with improved optics, the partner was spotted directly, a faint, bluish point close to the glare of the main star. It turned out to be a white dwarf, one of the first ever recognized. White dwarfs are the exposed cores of stars that were once like or somewhat heavier than the Sunday. After billions of years of fusion, they swell into red giants, shed their outer layers, and leave behind a naked, Earth-sized remnant made mostly of carbon and oxygen, or similar elements crushed into a degenerate state. The result is a sphere about the size of our planet, but packing close to a solar mass into that volume. A teaspoonful of its matter would weigh as much as a mountain. Sirius B is one of these stellar corpses. It is small enough that, if you could place it alongside Earth, it would be comparable in radius. Yet it bends nearby light and pulls on its companion with the gravity of a normal star. Its surface, though cooler than it once was, still glows intensely hot, with temperatures many times those found on the surface of the Sunday. Over eons it will cool and fade, but not yet. For now, it remains a bright ember, a reminder that stars die and leave remains. When you look at Sirius from Earth, you do not see that history. You see only brilliance. The softer, more human stories. Attached to it, the flood, the seasons, the role it plays in various mythologies all focus on the obvious. A light that returns, a beacon in the southern winter sky that can guide travelers and mark time. The grave beside it is quiet. On our map of nearby space, Sirius stands out because it compresses extremes into a small volume, a luminous, relatively young primary that will live fast and die sooner than the Sunday. A dense, compact secondary that has already burned through its main sequence life and collapsed. Together they form a binary that has already witnessed one stellar death and will, in the distant future, witness another. In conversations about habitable worlds, Sirius rarely appears as a serious candidate. There are reasons for that. First, the main star radiates so intensely that its habitable zone, the range of distances where a planet could, in theory, have liquid water on its surface, lies much farther out than Earth's orbit lies from the Sunday. At those distances, the orbital periods would be long. The dynamics of the binary would complicate stable orbits. A planet in the right temperature range would have to thread a narrow path where the combined gravity of Sirius A and B did not destabilize it over long timescales. Second, the lifetime of Sirius A as a stable, main-sequence star is relatively short in biological terms. The Sun has already burned steadily for over 4.5 billion years and has several billion more to go. A heavier star like Sirius A may only remain in such a steady state for a few billion years in total, possibly less. That is enough time for planets to form and for some chemistry to happen. It is less reassuring if one is looking for the extended, stable conditions that allowed complex life to evolve on Earth. Third, there is the simple fact that, despite extensive observation, no planets around Sirius have been confirmed. There have been claims of distant companions in the past, hints of perturbations in the orbit that might suggest additional bodies, and more recent infrared searches for cool, Jupiter-sized worlds. Nothing has stood up to repeated scrutiny. If planets exist there, they are either too small, too distant, or too poorly placed for our current instruments to pick them out against the glare. So, we have a system that dominates our sky, shapes our cultural imagination, and anchors the southern constellations. But that offers no solid evidence of any worlds that could host life as we know it. For a long time, brightness and importance were almost synonymous in human thought. The brightest stars were made into gods and heroes. Their patterns became signs, calendars, proverbs. Fainter lights were ignored or folded into the background. In that older way of seeing, if any star in the neighborhood were to have weight in our stories, it would be Sirius. Astrophysics reverses the emphasis. The most promising candidates for temperate, potentially habitable planets in our 20 light-year bubble are often small red dwarfs, barely visible without a telescope. Their light is weak, their names are technical catalog entries, they have no ancient myths attached to them. Yet they host the super-Earths and near-Earth-sized planets whose orbits fall into the right zones. Meanwhile, the brightest star in the night sky turns out to be a stage with no actors that we can see. In the spotlight at center is a star that will live briefly, surrounded by a glare that makes the detection of small worlds difficult. Off to the side is a corpse, still hot, still dense, circling in silence. There is a quiet lesson in that arrangement. We are drawn instinctively to the most obvious lights, the things that insist on being seen. We build stories around them and tie them to cycles in our own lives. In the actual structure of the galaxy, those lights may have little to do with the presence or absence of life. A star can dazzle and still be sterile. It can dominate a hemisphere's worth of night sky and still hide nothing but a grave and empty orbits. In the context of our 20 light-year map, Sirius is a kind of reminder printed in very bright ink. Distance and brightness do not translate into companionship. The nearest dazzling star is, as far as we can tell, a system whose most intimate secret is that one of its members has already died. If you go outside on a cold, clear night when Sirius is high and let your eyes adjust, you can see that its light wavers more than the others near the horizon, dancing in the unsteady air. It feels almost alive, as if it were flickering on purpose. That impression is an artifact of atmosphere and altitude. The star itself is steady. The flicker is in us, in the restless layer of gas we breathe, and in the way our eyes and minds respond to the brightest thing on the page. Behind that flicker, a white dwarf orbits in a long ellipse, unseen. The brightest light in the neighborhood hides a stellar grave, and from that grave there is no signal, no voice, only a kind of enduring, indifferent glow. Some lights shout by being bright, others draw attention by staying almost completely quiet. Ross 128 is one of the quiet ones. It is a small red dwarf in the constellation Virgo, a star so faint that you need a telescope just to see it at all. Based on precise parallax measurements, it sits a little over 11 light-years from Earth, close enough to count as a near neighbor in our 20 light-year bubble, but far too dim to have played any role in ancient sky watching. On a star chart, Ross 128 is just another designation, a catalog name in a sea of similar entries. Spectroscopically, it is an M dwarf, with a mass only a fraction of the Sun's and a surface temperature less than half as hot. It is technically a flare star, capable of sudden bursts of brightness, but its flare rate today appears low. The best models suggest it is an older, magnetically evolved dwarf, whose activity has calmed with age. That relative calm is what made it interesting. For years, exoplanet searches focused on red dwarfs because their low luminosity brings their habitable zones close in, making the gravitational tug of small planets easier to detect. But many of those dwarfs turned out to be violently active, throwing off flares and high-energy radiation so often that any close world would be battered. After Proxima Centauri showed us just how hostile such a star can be, astronomers began to look for a different kind of host, a cool dwarf with a quieter magnetic life. Ross 128 fit that description better than most. Using more than a decade of high-precision radial velocity data from the HARP spectrograph in Chile, a team led by Xavier Bonfils announced, in mid-November of the second decade of this century, the discovery of a planet around Ross 128. They called it Ross 128b. It was, by their measurements, at least a little more massive than Earth, likely rocky, and orbiting near the inner edge of what they defined as the star's habitable zone. The numbers, translated into ordinary language, sound almost modest. Ross 128b completes one orbit in just under 10 Earth days. Its semi-major axis is only a few percent of the distance between Earth and the Sun, placing it perhaps 20 times closer to its star than we are to ours. At that distance, the planet is almost certainly tidally locked, showing one face to its star at all times, while the opposite side sits in perpetual night. In terms of energy received, Ross 128b gets somewhat more starlight than Earth, does roughly a third more, depending on the precise models and assumptions about reflectivity. Depending on its albedo, the equilibrium temperature estimates range from values cooler than Earth's to values somewhat warmer, with several scenarios clustering around conditions that, on paper, could allow liquid water to exist somewhere on the surface. For a brief time, this combination of traits made Ross 128b a kind of counterpoint to Proxima b. Here was another nearby Earth-sized planet in a habitable zone. But this one, circling a star that flared less often, whose magnetic tantrums seemed less severe, it became common to describe it as a temperate planet around a quiet star, a place where, at least in theory, an atmosphere might survive long enough for interesting chemistry to happen. Yet, in the same way that our worst fears about Proxima's flares are extrapolations, much of our hope about Ross 128b rests on inference. We do not see the planet transit its star, so we do not have a direct measurement of its radius. We infer a minimum mass from the Doppler shifts in the star's spectrum, but the true mass could be somewhat higher. We estimate temperature based on how much energy reaches the planet and on guesses about reflectivity. But we do not know whether there is an atmosphere to trap heat or clouds to reflect light. Even the word temperate is conditional here. It means something like not obviously too hot or too cold, given certain assumptions. Not confirmed mild climate with oceans and rain. What Ross 128b does give us, more clearly, is a kind of silence. Because the planet does not cross the face of its star from our point of view, we cannot use transit spectroscopy, our most powerful current method, to probe any gases above its surface. Future telescopes might manage to tease out atmospheric hints by other, more indirect means, but for now, its air, if it has air, is beyond our reach. Likewise, any surface features, continents, clouds, or oceans it might host are hidden in the glare of a star that, despite being faint compared to the Sun, still dwarfs its planet in brightness by many orders of magnitude. And when we listen for artificial signals, the quiet deepens. In May of the year 2017, the Arecibo radio telescope in Puerto Rico picked up a strange broadband signal while observing in the direction of Ross 128. The signal was unusual enough that the observing team nicknamed it the Weird and shared their puzzlement with colleagues. For a few weeks, speculation rippled outward. Here was a nearby red dwarf with a potentially temperate planet. Here was an odd, structured radio emission coming from its line of sight. The coincidence was hard to ignore. Follow-up observations came quickly. Other radio observatories pointed at Ross 128, listening across similar frequencies. Additional data were analyzed. Gradually, a more mundane explanation emerged. The most likely source, it turned out, was interference from one or more geostationary satellites orbiting Earth, whose transmissions had happened to align with Arecibo's field of view at the time of the original detection. The angle of Ross 128, near the celestial equator, made that kind of overlap particularly easy. The weird signal turned out not to be weird at all. It was our own machinery, seen indirectly. In one sense, that resolution was a relief. The data fit a known pattern. The universe returned to being as we expected it to be. In another sense, it underlined how ready we are to hear voices where there are none. A little noise in a single observation, and the thought arises almost automatically. Maybe this is it. Maybe this is the first shout from a nearby world. Ross 128b did not shout. If it exists as a quiet, potentially habitable world, it did not use that strange moment to announce itself. What we heard instead was a reflection of our own technology and our own desire projected onto a patch of sky where, for now, the only confirmed signals are natural. Between Proxima Centauri and Ross 128, there is a kind of bracket around our hopes. On one side, a planet in a habitable zone around a star that behaves like a firestorm, frequently erupting in radiation that might sterilize its surface. On the other, a planet in a habitable zone around a calmer star, bathed in more moderate light, unaccompanied by constant flares, but hidden from almost every technique we know how to use. In both cases, the realities of physics and geometry keep us at a distance. If Ross 128b has an atmosphere, it might be moved by slow winds that redistribute heat from dayside to nightside, smoothing out temperature gradients. The permanent day hemisphere could be shrouded in dense clouds, reflecting a significant fraction of the incoming light and keeping the surface below cooler than a bare rock would be. The permanent night hemisphere might be a landscape of ice, or a place where air condenses and freezes, or a dark ocean under starlight reflected from the other side's clouds. All of these images are, at present, more like disciplined daydreams than maps. They are grounded in models of tidally locked climates, in our understanding of how atmospheres flow when heated on one side, in the thermodynamics of red dwarf illumination. They are not grounded in direct observation of Ross 128b itself. What we have, concretely, is a handful of numbers: a period, a minimum mass, an inferred distance from the star, a calculated range of equilibrium temperatures, and the knowledge that the star it orbits shows relatively modest flare activity compared to more active dwarfs. We also have the negative result of the radio follow-ups. No repeating artificial signals in the bands we have checked so far. On our 20 light-year map, Ross 128b sits in a strange category. It is close. It looks, from a distance, like one of the better candidates for a temperate surface among the nearby exoplanets. It has already been the subject of speculative essays about habitability, and yet, from every practical angle, it remains a cipher. We cannot see its air. We cannot see its ground. We cannot hear its technology, if any exists. All we can say with confidence is that there is a small planet tugging gently on a quiet star, moving in a tight circle every week and a half, bathed in light that is dim and red compared to our own sky. For some people, that is enough to call it hopeful. For others, it is just another entry in a growing list of worlds that could be interesting and currently are not. In the context of this map, it is something narrower and more instructive. It is a reminder that even the best candidates, the ones that check all the basic boxes of mass and temperature and stellar environment, can still be totally silent to us. A world can be close, calm, and perhaps even comfortable, and yet refuse, through no intention of its own, to send us any sign we are capable of reading. In that sense, Ross 128b is a quiet world that refused to shout not out of malice or secrecy, but because, so far, there is no shared language, no common channel, and perhaps no one there at all. A single quiet world is unsettling. A whole background of them is something else entirely. When we step back from the obvious names, the map inside 20 light-years begins to fill with stars that almost never make headlines. They are not the brightest in our sky. They rarely carry dramatic stories about strange signals or second Earths. They sit just under the threshold of public attention, doing the slow work of existing. Take 61 Cygni. To the unaided eye, in a dark northern sky, it is a faint, ordinary point in the constellation of the Swan. Through a small telescope, it splits into two orange dwarfs, each dimmer than the Sun, circling one another on an orbit that takes many human lifetimes to complete. What made this system important was not how it looks, but how it moves. In the early 19th century, Friedrich Bessel chose 61 Cygni as his target for an ambitious experiment. Measuring its tiny yearly shift against the more distant background as Earth went around the Sunday, the parallax angle he extracted was minute, but real. From that angle, he inferred that the star lay roughly 10 to 11 light-years away. It was the first time anyone had pulled a reliable distance out of the sky for a star other than the Sun. And it turned the word light-year from an abstraction into a measured span. Modern measurements place 61 Cygni a little over 11 light-years from Earth. An old, slowly rotating pair of dwarfs, radiating with a fraction of the Sun's luminosity. They are probably older than our star, with lower masses, cooler surfaces, and longer lifetimes ahead. The habitable zones around each component are tight, narrow bands where a planet could, in theory, receive the right amount of light for liquid water. Decades of monitoring have not yielded any confirmed Earth-like planets there. There are constraints, upper limits on possible planetary masses, hints, and non-detections. On paper, a small rocky world could exist in those zones and still escape our current instruments. In practice, 61 Cygni remains, for now, what it was in Bessel's time. A system we know mainly because it let us draw a first reliable ruler in space, not because it has offered any sign of life. Further south, Epsilon Eridani tells a different, quiet story. This star is closer to the Sun than 61 Cygni, at just over 10 light-years away, and bright enough that sharp eyes can pick it out from a dark sight. Spectrally, it is a K-type dwarf, slightly cooler and less massive than the Sun, but significantly younger, perhaps only a few 100 million years to about 1 billion years old. In stellar terms, it is still in its early adulthood, spinning faster, with stronger magnetic fields and more activity than our star shows today. Around Epsilon Eridani, astronomers have mapped out a dusty debris disk, a broad belt of cold material reminiscent of the Kuiper belt beyond Neptune. Embedded within or near that structure is a confirmed gas giant, Epsilon Eridani b, a planet with a mass on the order of Jupiter's, orbiting several astronomical units from the star on a timescale of several Earth years. Its discovery at the turn of the century and subsequent refinements in its orbit turned the system into a kind of laboratory for thinking about our own solar system's youth. A young star, a Jupiter analog, belts of dust and rock, and probably smaller, as yet unseen planets closer in. In public imagination, though, Epsilon Eridani never fully captured the role of second solar system. It is too obviously unfinished, too turbulent. The gas giant is cold and uninhabitable. The inner system, if it hosts smaller rocky worlds, remains unresolved. Models suggest that any habitable zone planet there, if it exists at all, would be bathed in the ultraviolet and X-ray output of a star that is still settling down, its wind and flares stronger than the sun's. It is an instructive place, not a comforting one. Move a little farther out, and the names begin to sound less familiar. Luiten's star, catalogued as GJ273, the red dwarf hosting Luiten b, the dim system called GJ1061 with its trio of super-Earths. Luiten's star is an M dwarf in the constellation of the Lesser Dog, at a distance of roughly 12 light-years. Its mass is only a little more than a quarter of the Sun's, its radius a few tenths, its luminosity less than 1/100th. To see it, you need binoculars or a small telescope. To the naked eye, it simply is not there. In the second decade of this century, radial velocity observations from the HARPS spectrograph revealed at least 2 planets around it. The inner one, Luiten b, also labeled GJ273b, is a super-Earth with a minimum mass almost 3 times that of Earth, orbiting close enough to its star that it completes a year in under 20 days. It receives only a small percentage more starlight than Earth does from the Sun, placing it squarely within many definitions of the habitable zone for such a cool star. On paper, that makes Luiten b one of the best nearby candidates for a temperate, rocky world. It is close. Its host star is reasonably quiet for an M dwarf, and its incident flux is not obviously hostile. We do not see it transit, so its radius and true mass remain uncertain. But the basic parameters line up in ways that are easy to like. Perhaps because of that, Luiten's star has already become a target for more than just passive listening. In the late 20-teens, a collaboration between artists and scientists sent a series of radio messages from a Norwegian antenna aimed specifically at GJ273b, a project called Sonar Calling. The transmissions included music and encoded information, timed so that if anyone were listening there with roughly our level of technology, they might detect the brief burst and recognize it as artificial. The signal will take a bit more than a dozen years to arrive. Any answer, if there was someone inclined to reply, would take just as long to come back. The odds of a conversation actually starting this way are extremely low. The project's value lies elsewhere. It marks a point on our map where we have not only identified a potentially habitable world, but also chosen to speak first, knowing full well that silence is the most likely response. GJ1061 is another small red dwarf, its name even less friendly to the ear, sitting at a distance of roughly 12 light-years in the southern sky. Radial velocity surveys have revealed at least 3 planets around it, all super-Earths in tight orbits measured in a handful of days. One of them, GJ1061c, receives roughly a third more stellar flux than Earth and may sit within the optimistic bounds of the habitable zone, given certain assumptions about atmospheres and clouds. Another, GJ1061d, farther out, has been flagged as a possible temperate world as well. These planets are not household names. They have not carried sensational headlines or been the focus of elaborate press conferences. They live mostly in catalogues and specialist papers, in plots of radial velocity curves and tables of orbital parameters. If you search for them, you will find artists' impressions, dark rocks lit by dim red suns, sometimes with oceans sketched in for effect. Outside those sketches and the math that underlies them, they are invisible. Around them and between them, the background fills with still more systems. Captain's Star with its debated planets, Groombridge stars with high proper motion and sparse planetary evidence, a scattering of K and M dwarfs that host 1 or 2 known worlds and might host more we have yet to discern. The count of planets within 20 light-years has grown steadily over the last 2 decades, from a handful to dozens. And yet the emotional landscape of that growth is not what popular imagination once assumed it would be. Instead of finding one obvious twin to Earth, we have uncovered a patchwork of partial matches. Here a planet with the right size but an angry star. There a calm star but a cold gas giant. Here a near-perfect energy budget but no way yet to look at the atmosphere. There an intriguing candidate whose very existence is still under debate. The background stars, the ones that do not dominate our sky, are quietly telling us that rocky planets in or near habitable zones are not rare, but that knowing they exist is not the same as knowing that anyone lives there. From a certain angle, this is what makes the nearby map feel most empty. The silence of a single system can be written off as bad luck. The silence of many different systems, under many different conditions, begins to look like a pattern. 61 Cygni, an old double star whose distance we mapped before we knew what a galaxy was, offers stable light and no clear worlds to catch it. Epsilon Eridani, a young analog of our system, hosts belts and a giant but no known temperate rock. Luton Star and GJ1061. Dim dwarfs hosting super-Earths in theoretically promising orbits sit under directed beams of our music and mathematics and do not, so far, answer. None of this proves that life is absent there. It only tells us that, with the methods and sensitivities we currently possess, the background stars are behaving as if they were alone. Taken together, they form the quiet underlayer of our 20 light-year bubble, a swarm of systems rich in orbital dynamics and modest planets, each with its own chemistry and history, each mindlessly precise in its motion. They rarely make headlines because nothing dramatic happens around them on human timescales. They are just there, dim and steady, filling in the space between the louder names. In an ordinary night sky, the eye is drawn to the few brightest points. In our map of nearby space, the real story is in the rest, in the many faint stars that, added together, define the neighborhood's character far more than the sparse handful of lanterns we happen to notice. The longer you stare at the background, the more one particular smudge of hope and correction starts to stand out. Gliese 581 lives there, in the constellation Libra, a small red dwarf a little over 20 light-years away. By naked eye standards, it is nothing. You will never see it without instruments. By exoplanet standards, it became, for a few intense years, one of the most argued over systems in the sky. The star itself is unassuming. It is an M3 dwarf, with roughly 1/3 of the Sun's mass and a few tenths of the Sun's radius. Its total luminosity, summed over all wavelengths, is around 1/100th that of the Sunday. Its surface temperature sits near 3,200 Kelvin. Cool and red. Its light shifted toward the infrared. It rotates slowly. Its magnetic activity for a red dwarf is low. All of that made it appealing early on. An old, relatively quiet star, where planets might keep their atmospheres for a long time. The first planet announced there, Gliese 581b, came in the middle of the first decade of this century. The HARPS spectrograph in Chile had been watching the star for years, measuring the tiny oscillations in its radial velocity as unseen companions tugged it toward and away from us. Out of that data emerged a clear periodic signal, a planet with a mass at least 15 times that of Earth, on a tight orbit lasting just under 6 days, hugging the star so closely that any notion of habitability was off the table. A hot Neptune, or a small Saturn, depending on how you imagined its composition. It was not the mass that turned heads. It was what came next. Within a couple of years, the same team announced 2 more planets, Gliese 581c and Gliese 581d, Planet C, with a minimum mass, roughly 7 times that of Earth, orbited in about 13 days, at a distance where, given the star's low luminosity, it would receive more stellar energy than Earth does, but not necessarily enough to guarantee a runaway greenhouse. Planet D, farther out, with a period of about 67 days and a minimum mass around 7 Earths, received only a fraction of Earth's light, but might, with a dense carbon dioxide atmosphere, maintain above freezing temperatures. In quick succession, headlines declared first one, then the other, as possible super-Earths in the habitable zone. Artists painted them as blue and green spheres under dim red suns. Popular articles asked whether we might one day see their clouds, or their continents, or the glint of starlight off imagined oceans. The actual situation was more ambiguous. Depending on the exact atmospheric composition and circulation, Gliese 581c might be a scorched, Venus-like world, too hot for liquid water at the surface. Gliese 581d might be a cold super-Earth, with any water locked under ice, unless greenhouse gases built up to extreme levels. Both planets were almost certainly tidally locked, with one hemisphere in endless day and the other in endless night. Even so, the notion of 2 potentially borderline habitable worlds around a single nearby star altered the tone of exoplanet surveys. For a moment, the neighborhood felt crowded with possibility. Then, a 4th planet was added, Gliese 581e, an inner super-Earth with a few Earth masses on a 3-day orbit, bathed in intense radiation, and clearly too hot to be promising. That one did not stir much excitement beyond the technical satisfaction of finding such a low-mass world with radial velocity alone. The real emotional spike came with the announcement of Gliese 581g. In the year 2010, a team led by Stephen Vogt and colleagues combined HARPS data with additional measurements and argued that they could see signals for not just the 4 known planets, but 2 more. One of those, labeled F, would have been a colder outer world. The other, Planet G, sat almost perfectly in the middle of the star's habitable zone on an orbit of about 37 days, with a minimum mass a little over 3 Earths. It was, on paper, as close to a Goldilocks planet as anyone had claimed so far. Not too close, not too far, around a nearby, relatively quiet star. Vogt was blunt in interviews. Given the ubiquity of life where conditions are right on Earth, he said, he personally thought the chances for life on such a planet were essentially 100%. The quote spread quickly. Gliese 581g appeared on covers, in documentaries, in lists of top 10 places to find aliens. For many people, it became the first truly plausible answer to the question, if there is another Earth-like world anywhere near us, where is it? But almost as soon as the announcement settled into public awareness, the argument among specialists intensified. The HARPS team, using their own updated dataset and analysis methods, reported that they could not reproduce the signals for planets F or G. Later re-examinations of the full radial velocity set with more sophisticated treatments of stellar activity and noise, concluded that the evidence for both planets was weak at best. Gliese 581 shows subtle variations in its spectral lines due to star spots and magnetic cycles. Those variations can masquerade as planetary signals if not modeled carefully. Over the next few years, paper after paper leaned toward a simpler configuration. 3, or at most 4, robust planets, with C, D, and E as the main inner companions, and B as the hot giant, while F and G faded into the category of disputed, likely spurious detections. Eventually, catalogues began to list Gliese 581G explicitly as unconfirmed, then as refuted. The super-Earth that had briefly been our closest other Earth dissolved back into noise. All of this played out while another, quieter experiment was already on its way toward the same system. In early October of the year 2008, at a deep space center in Yevpatoria, Ukraine, a 70-meter radio telescope turned toward Gliese 581 and transmitted a high-powered digital signal. The project was called A Message from Earth. Organized through a social platform, it invited people around the world to submit short texts, images, and simple content that would be bundled into a time capsule and beamed toward one of the newly discovered planets. Gliese 581c, at that point still widely described as potentially habitable. The transmission lasted only hours, but the distance it had to cross was measured in light years. At just over 20 light years away, any radio pulse aimed at Gliese 581 takes more than 20 years to arrive. The message from Earth signal left our solar system in less than a day. It will not wash over the orbit of planet C until the late 2020s. If someone were there, listening with antennas at least as sensitive as ours, they could, in principle, notice a sudden, structured, narrow beam of radio energy that had not been there before. By the time that signal reaches its target, our understanding of the system sending and receiving it will have changed several times. We now think Gliese 581c is almost certainly too hot to be comfortable in any Earth-like sense, likely more of a mini-Venus with intense stellar flux and possible runaway greenhouse conditions. Gliese 581d, if it exists as a proper planet rather than an artifact, probably sits near or beyond the outer edge of the star's habitable zone and might need extreme greenhouse conditions to keep water liquid. Gliese 581g, the supposed perfect middle child, is more likely a phantom of incomplete modeling. In other words, we picked a target before the map was clear. From one perspective, that looks reckless. We aimed a message at a world we did not yet fully understand, under the assumption that in the habitable zone meant a reasonable place to say hello. From another perspective, it is exactly what humans do. We rarely wait for complete information before reaching out. The urge to send something, anything, to mark our presence seems to outrun our caution. If you imagine a vantage point around Gliese 581 with instruments as good as ours, looking back at the sun, the picture becomes stranger. They might see our star as a modest yellow dwarf with at least one giant planet and several smaller ones. They might notice that one of those small worlds has an atmosphere rich in oxygen and trace methane. They might, with enough patience, pick up the haze of our own radio leakage, a sphere of noise expanding at the speed of light. And, if they happen to be listening at the right time, in the right direction, with a narrow enough bandpass and enough luck, they might hear a sudden, brief amplification of that noise along one axis, the message from Earth signal leaving us, crossing the Gulf, and sweeping past them. Would that signal make sense to them? If they existed, the contents are parochial. Jokes, photos, snippets of culture, fragments of language, artifacts of the moment when the message was compiled. Even for us, if we were to receive something similar from another star, decoding it would be a slow, uncertain process. Recognizing its artificiality would be the main step. Understanding its meaning would be a separate, much harder task. What the Gliese 581 episode really highlights is less about the target and more about us. On the detection side, It shows how eager we are to call a world Earth-like on the basis of a handful of orbital parameters and minimum masses, even around stars that are quite unlike our own. We knew, intellectually, that red dwarfs are cooler, dimmer, and often more active. Yet the phrase, "in the habitable zone," was enough to trigger a cascade of hopeful projections. On the retraction side, it shows how unforgiving the data can be once methods improve. Planets that once carried full conceptual lives in the public imagination can be demoted to noise, their existence downgraded from almost certain to probably not. Not because anyone lied, but because the star's own subtle variability was more complicated than early models allowed. On the messaging side, it shows that we are willing to send a deliberate signal into that uncertainty anyway, knowing it may arrive at a place where no one is listening or where the environment is far less welcoming than early headlines implied. Within our 20 light-year bubble, Gliese 581 is therefore a special kind of dead world map. It is a system where our hopes climbed quickly and then had to be pulled back down. It is a system where we pointed a radio telescope and sent a capsule of human thought toward a planet that might be a hot, tidally locked super-Earth under a red sun with no oceans and no listeners. It is a system that reminds us that habitable is a sliding, model-dependent word, and that silence can mean many things. No life, hidden life, or simply the long delay between sending and the possibility of any reply. Sometime soon, by our calendars, the signal from 2008 will cross the orbit of Gliese 581c. No one on Earth will notice anything when that happens. There will be no sound, no flare of light, no return echo. The only record will be in our timelines and in the equations that tell us how fast radio waves travel. We will keep revising the orbits, the planet counts, the habitability assessments. The star will keep burning faintly in Libra, an old red dwarf with a handful of close companions, almost certainly quiet. And somewhere between the equations and the silence, a beam we sent years earlier will continue on its path. A thin line connecting one possibly dead world with another that is, for the moment, very much alive. The line between our living world and that faint red star is only radio and patience, but it is enough to remind us that maps are made of choices as much as of facts. If you pull back from Gliese 581, from Ross 128, from Proxima and Sirius, and the slow ghosts of Barnard's star and Wolf 359, the 20 light-year bubble reappears. Just a sphere in the dark, centered on the sun, dotted with a few dozen systems and a larger handful of stars and brown dwarfs. A neighborhood, in the weakest sense of the word. Inside that sphere, by now, we have identified scores of planets. Some are hot giants that skim the faces of their stars in a matter of days. Some are super-Earths in tight, quick orbits. Some live in the narrow regions, where models say liquid water might exist if the right atmosphere formed and survived. A few of those have names that briefly leaked into public speech. Most remain as catalog codes and plots in specialist journals. From all of them, across all the years that we have been listening, there has been no unmistakable sign that anyone else is building radios. That does not mean there is no life there. The silence rules out something narrower and more technical. No one within 20 light years is doing exactly what we are doing, at exactly the same technological level, in exactly the wavelength bands and time windows we have checked, with a power output at least comparable to ours, and in a way that points even briefly in our direction. Within those limits, the map is silent. That silence is already information. If advanced civilizations that like to shout with radio or lasers were common in both space and time, the odds that none of them would appear in such a nearby volume would be low. The fact that our immediate neighborhood contains only quiet stars and uncommunicative planets pushes some possibilities down the probability ladder. It nudges us away from the comforting idea that the galaxy is teeming with eager broadcasters on every scale and that we just happen to have missed them so far. At the same time, the constraints are far from absolute. The way we listen is narrow. The time we have spent listening is short. The forms that technology might take are wider than our current imagination. There are at least 3 broad possibilities hiding in this silence. The first is the coldest. Perhaps most worlds really are dead. In this picture, the Sun and Earth are statistical flukes. Chemistry has had billions of years and countless combinations to work with, but the exact pathway that led from simple molecules in our oceans to cells, and then to nervous systems, and then to nervous systems that ask about maps is rare. Most planets never even get to the first step. Their surfaces freeze or bake. Their atmospheres are stripped. Their water, if they had any, is lost to space or locked in rock. The few places where life does emerge may remain microbial for as long as their stars shine. Complex, technological cultures are vanishingly unusual. If that is true, then the 20 light-year bubble is almost exactly what we should expect. A handful of stars, mostly red and small, with more or less interesting geology on some of their planets. No radios, no beacons, a map of dead worlds punctuated by exactly one noisy exception, us. The second possibility is quieter but less bleak. Perhaps the universe is not empty. Perhaps we are simply very early in the part that knows how to talk. The age of the Milky Way is measured in something like 10 billion years. Our species has existed for a few 100,000. Our use of radio for deliberate, far-reaching communication spans barely more than 1 century. On this timescale, we are a first whisper in a long night. Maybe the chemistry that leads to life takes time to get started around many stars. Maybe metallicity and heavy element enrichment had to reach certain thresholds before enough rocky planets with the right compositions could exist. Maybe the kinds of long, stable climates that allow intelligence to evolve are rare now, but will become more common as the galaxy ages and the most violent epoch of star formation and explosion fades into history. If that is true, then our 20 light-year map is like an early survey of a city being built. We are walking through empty plots and half-built structures at dawn before most of the lights have turned on. The fact that no one else is waving from their windows yet does not mean the buildings will stay unoccupied forever. The third possibility is the most slippery. Perhaps the universe is full of voices, and we are simply deaf to the ways they speak. We built radio because it made sense given our atmosphere, our physics, and our history with lightning and antennas. We search for narrowband signals because they stand out against natural backgrounds. We look for spectral signs of oxygen and methane because those gases on Earth are tied to biology. But there is no guarantee that another technological species, with a different environment and history, would choose the same modalities, or that their signals would remain strong and obvious for more than a thin slice of their timeline. They might communicate mostly with tight, secure beams that never graze our orbit. They might encode information in polarization structures or neutrino fluxes or other channels we barely monitor. They might have long since moved past radio altogether, leaving only a faint archaeological layer of leakage that has already passed us by. Or, of course, they might exist mainly in times we do not share. Civilizations could rise and fall on timescales of tens of thousands of years, which sounds long to us but is a blink in stellar terms. Two such cultures in the same spiral arm might never overlap in time, even if they pass within a few dozen light-years of each other in space. From within our small, present moment, there is no clean way to choose between these possibilities. What we have is this: a map of the stars around us, a list of their planets, a growing set of upper limits on radio power and atmospheric composition, and the unmistakable fact that so far, the only place where we have seen physics turn into biography is here. There is a temptation, in the face of that, to force the conclusion, to say either, we must be alone, or they are definitely out there, hidden. Both are more than the data support. The honest answer is narrower and more unsettling. So far, within 20 light-years, all the evidence we have points to us being the only technological civilization that is currently loud in ways we know how to hear. That is a local statement, not a cosmic one. It does not tell us about the other side of the galaxy, or about other galaxies, or about the deep future. But it does tell us something about the scale that matters most to human planning and fear and hope. The distance we might conceivably cross in a time scale we can imagine. In this region, in this era, when we look for neighbors, we see only stars, planets, and our own reflection. It is easy to read that as isolation. It can also be read as a kind of responsibility. Every arrow we have drawn from Earth into this map carries both science and something more personal. The Voyager probes, slipping outward with their gold records, are repositories of data and of music. The message from Earth to Gliese, 581c, the artistic broadcast to Luton. B. The careful listening campaigns toward Proxima and Ross 128. And the background dwarfs each of these is, technically, an experiment. Each is also an expression of refusal to let the universe be a one-way monologue. On a diagram, you could draw them as thin lines radiating from the Sun, crossing the orbits of our own planets. Then the invisible spheres of influence around other stars. Some are just beginning their journey. Some have already passed the distance where Pluto orbits. Some will, in tens of thousands of years, drift through other systems entirely, long after the civilizations that launched them are gone or transformed. However you feel about the wisdom of sending messages, they mark something important about the only world on this map that definitely is not dead. We are not just listening. We are writing on the dark. Seen that way, the 20 light-year bubble is a double map. One layer is the stark geography of dead or silent worlds. Proxima b locked to a flaring dwarf. The uncertain or absent planets around Alpha Centauri, the erased echoes of Barnard's star B. The quiet candidates around Ross 128, Lytton's star GJ 1061. The bright indifference of Sirius and its white dwarf. The red stillness of Gliese 581, with its rescinded second Earth. Descent, Martian splash to sprays. The other layer is a record of what a single species did when it realized how empty its surroundings appeared. It tuned receivers. It built instruments that could measure wobbling starlight to a few meters per second. It sent probes to the edge of its own star's wind. It carved music and diagrams into metal and flung them outward. It pointed big dishes at red dwarfs and listened through the static. The question that remains, at the edge of this map, is less, is anyone out there? And more, what does it mean to be here at all? In a place that looks this quiet, maybe we are alone in this volume for now. Maybe we are early, a first bright noise in a galaxy that will, over billions of years, grow louder. Maybe the others are talking in ways we have not even thought to check. All of those may be true in different places and times. What the 20 light-year bubble does is force us to confront a simpler, immediate choice. To every distant observer who might one day draw their own map, the Sun will be just one more star. If they ever resolve Earth as a point of light, they will see only that our atmosphere is out of chemical equilibrium, that our nights shine more brightly than they should, that a thin shell of radio noise expands around us. They will not see our arguments over how to name planets, or our doubts about whether to send messages, or our late-night videos about dead worlds. To them, if they exist, we will fall into one of only two categories: another silent rock, or a place that tried to speak. You are watching this in a narrow sliver of time when that is still undecided. We have only just begun to map the neighborhood. We have only just begun to decide what to do with what we see. If, after this, you find yourself looking up at the night and feeling the size of that quiet bubble around us, you are already part of the answer. What we do next, what signals we send, what worlds we choose to listen to, what kind of trace we leave on this small map of dead and living worlds, is not a question the universe will solve for us. It is a decision we make, here, together, on this one noisy planet. And if you want to keep walking through that darkness, to keep unfolding this map of nearby silence one faint star at a time, you are welcome to stay.